So in this video, I am going to solve this problem. A battery of EMF 12 volts and internal resistance 1.5 ohms is connected to an external resistance of 3 ohms. Find the current flowing in the circuit. So let's see the solution to this problem. Here in this question, we can use diagram to represent the information here and then interpret it with formulas, then solve it. A battery having 12 volts of EMF. EMF represents or stands for electromotive force. And electromotive force is the force that sets an electrons on motion. Alright, so a battery of EMF 12 volts. So it is just like having a battery of this kind. This is a battery or a cell, and then an internal resistance. So we have an internal resistance like this. It's connected to an external resistance. So this is the connection, and this is the external resistance. It's not really compulsory you should draw the diagram to represent the information before solving. You can as well solve the problem without the diagram. I just want to show you what is really happening in this system. So if this is positive and this is negative, and the battery has 12 volts, the internal resistance is 1.5 ohms. And then it's connected to the external resistance that has 3 ohms. It is expedient that you should understand that this particular voltage, or the EMF, is different from the output voltage or the voltage across this resistor. I think it's better we should understand that here, whenever we have a cell or an EMF, it usually has its own internal resistance alongside with it. That's why we usually use small letter arrow to represent this, and this could be capital letter arrow. Alright, sometimes you can take this as the load resistor, because this is a load, and when it is connected to the battery, there are a lot of things that happens. A current is expected that the current flows from this direction. The current flows from this. This is a positive and this is a negative, and current always flows from the positive terminal of the cell or the EMF and terminates at the negative. So in this case, we can also have at this point we will also have what we call the voltage across this resistor, which is V subscript arrow. All right, this is a voltage across the resistor, and this voltage can also be calculated by using the formula for Ohm's law. And Ohm's law states that the current passing through a metallic conductor is directly proportional to the potential difference. All right, so from Ohm's law, we have this expression this way. Okay, for us to be able to calculate this, it's simple. We can as well apply voltage, the Ketchup's voltage law. Ketchup's propounded 2 laws in electricity. One is the Ketchup's current law, and another is the Ketchup's voltage law. The Ketchup's current law states that the algebraic sum of current entering a junction is equal to 0. Or you can still define that Ketchup's current law as the current. Let's represent it shortly. In Ketchup's current law, if this is the source voltage or the source that delivers all this current, let's say this one is entering, these ones are entering, and these ones are leaving. All right, this is I1, I2, I3, I4, and I5. You can see the indication of this arrow. This 3 is indicating that the currents are entering into this source, and this 2 is indicating that the currents are leaving. So Ketchup's current law states that the algebraic sum of these currents is equal to 0. That means if I have I1 plus I2 plus I3, and I can still add them up and take them across, or still take the negative or the, because these ones are leaving, so they are acting opposite. We can have this as a minus I4 minus I5 equal to 0. What does that mean? It means the algebraic sum of this current is equal to 0. That's Kirchhoff's current law. Then the Kirchhoff's voltage law is talking about the sum of the Kirchhoff's voltage law is talking about the sum of the voltage drop. And what do we mean by voltage drop? We have voltage drop to be I times R. So you can literally have the EMF minus the current times the resistor. The current multiplied by the resistor is what we term as the Kirchhoff's voltage law. Okay, it's what we call the voltage drop. Yeah. So this expression demonstrates Kirchhoff's voltage law, which I can still use this to solve this problem. But to keep things simple, because of the level of students I'm making this video for, which are SSCE or WIC students or pre-degree students, I'll have to use a familiar formula that they can be able to easily access. Then in advanced class, we'll apply the voltage or the Kirchhoff's current law to solving problems related to this. All right, so the simple formula I will use here is this. Since in this particular cell we have the internal resistance, and then we have this load resistor all over there, so we were able to mix up these things together and calculate the current, because you check the instruction, they say you should find the current flowing in this circuit. In the video, I'll be talking about the internal resistance, the explanation of the internal resistance. Then I'll be able to tell you if a current or if a voltage of 12 volts is produced, what happened to the current? Is the value of the current going to increase, or is the value of current going to decrease, or what happened to this particular voltage across the load resistor? All of these we're going to explain them. All right, in the next video I'm going to upload on internal resistance. So solution to this problem is this. Hence we are calculating for the current. There is a relationship between the current, the internal resistor, and also the EMF, and then the load resistor. And that formula is put together with this expression having E equal to the current multiplied by this plus the current multiplied by this particular one. So this is the relationship between them. So in order for me to get this current, I'm going to look for the common expression or common factor here, which I is common to both sides. I'll factor I, then I'll have R plus capital letter R, which is a load resistor. So in this case, I can easily make the current the subject of the relation, because that is what I'm looking for. So I can say I at this point, dividing both sides by this coefficient or this particular factor, yeah, or this function, R plus this. I'll divide both sides by this, so I'll have E all over R plus capital letter R. So this is the expression I will use in solving this problem. So at this point, what is our E? Our E is the EMF, which is 12 volts. So I have it to be 12 divided by what is our small arrow? Our small arrow, which is internal resistance, is 1.5 plus what is the value of this load resistor? That is 3. So let me get calculator and add up this together. So in a bit to sorry, I believe by now you would have added up this and then put down the answer to this in the comment section. However, let's do it together and then have the answer fixed here. So we have the denominator of this expression to be 1.5 added to 3, and the result to this is 4.5. Therefore, the current will be equal to 12 divided by 4.5. And we have the answer to be 2.66666667. So we just need 2 decimal places. So we have 2.67, approximately 2.67. So what is the SI unit of current? The SI unit of current is amps or ampere. So that is the solution to this problem. So alternatively, for those of you who are familiar with Ketchup's voltage law, you can still use this expression to solve this problem. And then when you use this to solve it, drop the answer in the comment section. Let's see if it will still give you the same result. Those of you who also are familiar with Ketchup's Ohm's law, you can still use this expression V equal to I arrow. Alright? And then make I the subject of the formula, which is V all over arrow. What is this arrow? This arrow we have here is the equivalent resistor. How do we get this equivalent resistor? Notice that this and this are connected in series. There's no break, so they are connected in series. So serial resistor is the summation of this, and that is arrow plus capital letter arrow. And this V is for the voltage. Voltage is the same thing as EMF. They are all measured in volts. And same thing with the potential difference. They are all in volts. So at this point, you can see that I will be equal to, so this is 12 all over 1.5 plus 3. And if you sum it up, it will still give you the same result. Try it. And then drop the comments, drop the information you have in the comment section. And like this video, subscribe to our channel if you've not done that. If you've subscribed, then stay subscribed. And also make sure you share at the time you're done watching the video and if it makes sense to you. Thank you very much. And for all of these and more, I'll see you on the next video.